Today I'm going to show you how the stack window works in the EZ68K simulator. I have opened tutorial 4 in the editor assembler. It comes with every installation of EZ68K. What this does is it uses two subroutines to add two numbers together. One that uses registers, which we're not interested in, and the other that uses the stack. So before we start, what is a stack? A stack is a last in, first out data queue that exists as a data structure somewhere in memory. What does that mean? It means that it's a data queue that where the last item pushed onto the stack is also the first item pulled out. Think of it like a stack of books. The last book you stack on the top is also going to be the first one you take off, unless you want the whole thing to fall over, but that's irrelevant. The stack exists the stack only deals with 16-bit and 32-bit numbers. No bytes are dealt with here, longs and words only, and it grows towards lower addresses. What does that mean? Well, that means that the last item pushed onto the stack will have a lower address than the item before it. So today I'll show you how to view the stack window, push an item onto the stack, pull an item off the stack, and create what is called a stack frame for use in subroutines. So I'm going to jump right into it here, and I'm going to assemble and execute, and up pops the simulator. In order to view the stack, we'll go up to View and Stack. Here it is. Right now, there's absolutely nothing in it. We are at location 0. This View menu right here, SS, will always point to the current stack pointer, and that's exactly what it sounds like. It's a pointer that points somewhere in the stack. That always shows up as yellow. You can also, the stack pointer is also address register 7. You should never use A7 for anything else except for the stack pointer. You can also view any other address register pointers in here. Right now there will all be 0, but all the other address registers show up as a tealish, baby bluish color. We'll go back to the stack pointer. So I'm going to run the program. Actually, let me rewind that. I'm going to go through and I'm going to put a breakpoint in after the first subroutine that just uses registers, but right before we push the new item onto the stack, because we're not interested in the registers, so we'll just skip through that subroutine. 6, 7. Okay, now we're into the stack. I'm going to add the number 8. 8. So what that did is it performed the trap task to receive a number from the keyboard, stored it in D1 as a long. Well, yeah. So this code right here that I've selected where my breakpoint is, it is going to, I'm going to put a couple more breakpoints in here. It's going to take what is in D1, which I just entered as the number 8. You can see that up here at the D1 register. And it's going to decrement the stack pointer. Remember earlier we said stack grows towards lower addresses, so you want it the stack pointer to go down to go to the top of the stack. And then it's going to push the number 8, the long word 8. Oh, I'm sorry, yeah, the long word 8 onto the stack. I'm going to step over. We'll view our stack. Stack pointer. You can see here the number 8 is at the very bottom of the stack, which is actually the top of the stack. And we reserved room for another long word because the stack pointer is currently right here. So we have this whole long word is reserved for the number 8. So next we'll step over again, step over again, step over again, step over again. Now it wants another number. We will use the number 4. I'm using small numbers like this because their hex values are the same as their ASCII values, so it's easier to tell what they are in the stack window. Number 4. As you can see right here, before we push it on it's still just the number 8, but it's going to do the same thing. Take what's in D1, decrement the stack pointer for enough room for another long, and then push the number 4 onto it. So step over. There it is. Here's our long word 8. Here's our long word 4. With the stack pointer pointing with enough room for another long word because we decremented it. So now we're going to push the literal number 0 onto the stack in order to create room for the sum. Again, it's going to be a long word, so we should see that go right above this 4. See. Step over. There it is. We have our 8. We have our 4, we have our 0. I have now put in a breakpoint at the adder2 subroutine to show you how stack frames work and how you can pass variables to a subroutine using the stack. So I put a breakpoint right here on the link instruction. The link instruction takes a address register and creates a stack pointer out of that never moves, that can only be used by the subroutine. It also takes a literal number to tell how many bytes to save for this stack frame that can be used by this subroutine. For this particular subroutine, we're using 0 because we don't actually need to save any data in this subroutine. We just need the A0 pointer. So if I go over here into the stack window, you can see SS, which is the stack pointer, is pointing right here at location F0 above our 8, above our 4, and above our 0. Now this number added in here, this 1072, is the return address that the BSR or RTS instruction in the subroutine will tell that where to return to once we are done with this subroutine. As you can see here, it's 1072. If we look here in our program, 1072 is the location directly after our adder2 subroutine call, so it knows to return right back to there once this is done. So if I step over, we can see that we have now created where we have moved above the return address and created what's called our stack frame. If I look here in A0, they're both pointing at the same location right now, at location FEC, right above our return address. If I step over again, we're going to move D0 into the stack and decrement it, and decrement the stack pointer. So we'll step over again. Now, A0, if I go back to the stack pointer, SS is our stack pointer, and it's pointing at FE8. And there's our 4. We move D0 into the stack. Now if I click here and look at A0, the stack pointer is now yellow. It's still at FE8, and this A0 is still in the same location we created it at, FEC, right below it. Like I said, A0 will never move. That's just used as somewhat like a reference point so you can know where to access variables on the stack from this subroutine. Unlike the stack pointer, that will never move. So if I step over again, now this instruction is going to take num1 and put it into D0. And the way that it knows how to do that is, if we look up here where we declare our variables, there is an offset 4 plus 4. The first 4 is 4 bytes for the return address and 4 bytes for the actual A0 variable. So it knows not to look in either of those because it knows that's where it knows those are taken. So it's 4 plus 4, and then it's going to go here, sum plus 4, so that's 12. 4 plus 4 is 8, plus 4 is 12, plus 4 is 16, and it's going to come down here to num1. So it's going to know to look 16 places, num1, because of our offset and our other variables. So 16 places from A0 and store that in D0. So 16 places from A0 would be 4, 8, 12, 16. Or I'm sorry, 4, 8, 12, 16. So we're going to store the 8 into D0, and there it is. There's our 8 in D0. Next, we're going to move 12 places from A0 to store it in D0. Same reason. We have our offset, which is our return address, and our storage for A0, which is 8, and then 4 more for sum, so it knows to look past that, and then move to num2, which is 12 spaces from where A0 currently is, which, as I said before, never moves. 4, 8, 12. There's our 4. So now we're going to add our 4 into D0. Step over, and there's C, which is 12. So it added 4 to D0. Now we are going to store our result where we saved that 0 earlier, above our 8 and above our 4. And all that is going to do is say move 8 positions from A0 and store D0 there. 4 plus 4 is 8 for our offset. move it right here into sum, which is what we did. So move it some positions from A0, which is 8, which we should see that appear right above our 4. That's where we declared it earlier. Step over, and there it is. There's our C, which is 12. Now we're going to restore D0, so we're going to increment our stack pointer by 1, well, by 1 long, and store that, whatever it's at after that, into D0. So if we look here, our stack pointer is currently there. We're going to increment that by 1 and restore D0 to that. Step over, and now it's our D0 is 4. Step over, unlink is going to basically get rid of our A0, get rid of our stack frame, get rid of everything that we just created here. Going to step over again. Oh, and we restored D0, by the way, because we are not passing our parameter with D0. We need D0 to equal what it was. We're not using the registers. We're passing it using the stack. And if you look here at location F4 over here, our sum 4 plus 8, 12 is still right here, right under our return address, C, right there. So that's why we restored D0. We're not passing it with the registers, we're passing it with the stack. So if I step over again, now our stack frame is unlinked. See, A0 is now down here because there is no A0. It's at location 0. We unlinked it. A0 is not there anymore. We don't need it anymore. It's gone. But our stack pointer is still here at the return address at 1072. So we'll view the stack pointer again. I will step over again. And now, since we went through our return address, we returned. It went down 1 to where our sum is, C, 12. We're going to increment the stack pointer by 1 long and pull that off and put it into D1. So we're going to increment this and grab the C, which is 12, and store that right here into D1. Step over, there we go. Now we're back at location F8, where our 4 is, our num2, D1 is stored, has our sum stored in it. We're going to clean up the stack a bit, which if I step over, I can show you. All that does is put our stack pointer back at 0. All of our stack information is still there. We didn't erase anything, but our stack pointer is now back at 0. So if we were to do anything else with the stack, remember the stack grows towards smaller addresses. So it's going to grow upwards, and we can overwrite whatever data we have in here. And then if I just finish the program here, step over, step over, step over. This just displays the strings. There's our sum is string. And now, since location or register D1 is storing our sum, trap task number 3 stores whatever number is in D1, a long number. We will be able to display our sum. And there we go. There's our 12. So that is how you can use the stack for many different ways. For storing information, for passing data to subroutines, and and that is how you use your address registers to figure out where everything's pointing. I hope this tutorial was very helpful, and thanks a lot for watching.